In this video, we're going to take a look at a couple more functional transforms, which we can find using that basic Laplace transform equation that we labeled equation 1 in a previous video. So let's first look at a decaying exponential function. And so we're defining this for t greater than 0, so we can write this as e to the minus at u of t. And we're assuming a is just some constant value, and if it's actually decaying, of course, a is going to be greater than 1. So let's find that using our equation. So we come and we can say our Laplace transform of e to the minus at u of t. And again, this u of t is sort of just an explicit formality saying that this function is defined for t greater than 0. So what we have then is we have our integral from 0 minus to infinity. And as we saw on this range with our previous video, our u of t is just 1. So we have 1 times e to the minus at times e to the minus st dt. Well, if we are multiplying these two things with exponents, we can then add the exponents. So we have integral from 0 minus to infinity of e to the negative a plus s times t dt. And from here, our evaluation is going to look pretty similar to last time. It's just our argument of our exponent is different. So we have a negative 1 divided by a plus s from considering our chain rule when we do that derivation. And that's multiplied by e to the negative a plus s t. All of that is evaluated from t equals 0 to infinity. Plugging in those values, so at t equals infinity, again, we have e to the minus infinity, which is going to give us 0, minus, and then we evaluate at t equals 0, and again, that exponential term e to the 0 is just going to be 1. So we're going to have negative 1 over a plus s times 1, and so that's our second transform pair. So now we have this e to the minus at times u of t, and again the u of t is just explicitly defining it for t greater than 0, and we're saying that the Laplace transform pair of that is 1 divided by s plus a. So let's take a look at another common function, our unit impulse function. And so our unit impulse function is our delta of t. So this is just, if we're looking at a plot over time, we just have an impulse here at the origin, so at 0, and the area is 1. And so typically we'll just write a 1 next to it. So this is kind of a mathematically interesting thing. Our delta function, it's not necessarily the height, but mathematically we'll typically draw it as varying heights that represent the area. So let's not worry about that for now. But basically what we're going to do is we're going to use something called the sifting property. So let's use the sifting property, which you might be familiar with from a calculus class. And so what our sifting property says is that if we have the integral from negative infinity to infinity of f of t times delta of t minus a dt, that's just equal to that function evaluated at a. So basically it's our function at whatever point the delta is at. So with that in mind, let's write our Laplace transform equation. So we have the Laplace transform of delta of t is equal to the integral from 0 minus to infinity of delta of t times e to the minus st dt. And so we see the limits on the integrals are different. We don't really need to be too concerned about that because our delta here is falling within the range of our limits. So we're not worried about having different limits for our integrals. But following this basic formula above, we can see for this case down here, our a term is 0, so we don't have any value there. So with a equals 0, our f of t in this case is this e to the minus st, so we have e to the minus s, and now our t is 0. So of course that's just e to the 0, which is equal to 1. So for our impulse function, delta of t, we now have the Laplace transform pair that goes to 1 in our frequency domain.